Hello students, welcome back. Today we're going to be studying the linear approximations and differentials. So we already studied a little bit about linear approximations when we were learning about the derivative, right, and properties of the derivative. So let's remember, when we're trying to do a derivative, we're trying to find the slope at the point, right, and that slope at the point would give us essentially a value, right? So this is essentially going to be our linear approximation. So the tangent line, or in other words, the linear approximation, can be written as the following equation. Okay, so this is linear approximation in the point. So in other words, right, we can rewrite it, right? It was approximation to function, but now I'm going to approximate it as L of x, right? So L of x, let's rewrite it. So L of x is going to be f of a plus f prime of a times x minus a. Okay, so now if we would like to approximate the function, we can now approximate it through a derivative. So let's take a look at an example. So the first example here is we want to find a linearization function f of x equal to x plus 3 at a equal to 1 and use it to approximate the numbers 3.98 and 4.05. Are these approximations overestimates or underestimates? Okay, so now let's go ahead and rewrite it. So we can have f of x to be x plus 3 to the power of 1/2. So f prime of x, right, is going to be 1/2 times 1 over square root of x plus 3, right, by the power rule and the chain rule. So, right, we know that a is equal to 1, so f of 1 is equal to, so if we compute it, it's going to be 2. And then f prime at 1 is going to be 1/4. So, plugging the values into the formula 2 for the linear approximation, which is f of 1 plus f prime of 1 of x minus 1, we will get 2 plus 1/4 of x minus 1, which is equal to 7/4 plus x over 4. Okay, so corresponding linear approximation at the point a equal to 1, so square root of x plus 3, is approximately 7/4 plus x over 4 for x near 1. Okay, so if we evaluate square root of 3.98, that means our x is 0.98, so it's approximately 7/4 plus 0.98 over 4, which is equal to 1.995. And likewise, we can do for square root of 4.05, which is approximately 7/4 plus 1.05 over 4, which is equal to 2.015. Alrighty. So the actual values, if we start to approximate, right, is we start to actually write them down. So the actual values. So we got these values, right? And we have slight overshoot, right? We have slight overshoot for both cases. So, but we do have a pretty good approximation, right? We have pretty good approximation. So now what we can do is we can ask the following question. Well, how accurate are our approximations? So let's go ahead and ask this question. So for what values of x is the linear approximation that we found in the previous problem accurate to within 0.5? And what about accurate within to 0.1? So essentially, what we can do, we can write it as square root of x plus 3 minus 7/4 plus x over 4 less than 0.5. So that means that's equivalently equal to same thing as square root of x plus 3 minus 0.5 less than 7 over 4 plus x over 4 less than square root of x plus 3 plus 0.5. Okay, so this says that the linear approximation should lie between the curves obtained by shifting the curve y equal to square root of x plus 3 upward and downward by the 0.5 amount of units. Okay, so essentially, right, we can imagine it like this, right? This would be the graphical representation of what we've done. So we shift it upwards and downwards. So this is our accuracy, right? This is our actual, right in the middle, and this is our gap, essentially, of accuracy. Okay, and then same thing. So as we decrease the gap, right, we're going to have smaller and smaller points that we can actually obtain within that accurate range. So now, points so the distance have decreased, so the points P and Q now became closer to the actual point. Okay, perfect. So this is actually very common to use in physics, right? So physics, linear approximations, so sometimes there are going to be some differential equations that are going to be too complicated to solve analytically, meaning that because of their nonlinearity, we have to approximate, right? One of the famous approximations that we can make is as following, right? So when x is very small, right, far less than 1, sine of x is approximately same thing as x, right? And the linear equation actually will describe, near 0 will describe the same behavior as sine of x. Okay, perfect. So that leads us to a new idea, the idea of differentials, right? So it's essentially the ideas behind linear approximations are sometimes formulated in the terminology of differentials. So if y is equal to f of x, right? So let's go ahead and write down. So differentials. So y equal to f of x, where x is a differentiable function. Then the differential, dx, is an independent variable. So we can write it as dy is equal to f prime of x dx, right? So dy is a dependent variable, and it depends on the value of x and dx. So essentially, that's how the derivative is occurring, right? And remember this following graph. So if we get this, okay. So we have this graph. So here we have the dx of delta x and dy, right? So this is our differential. Okay, so an example, right? Let's take a look at an example here. So we want to compare the values of a function. So compare the values of delta y and dy if y is equal to f of x equal to x cubed plus x squared minus 2x plus 1, and x changes a from 2 to 2.05 and b from 2 to 2.01. So for part A, f of 2 is equal to 2 cubed plus 2 squared minus 2 times 2 plus 1 is equal to 9. So f of 2.05, doing the same thing, but now we're going to use the calculator. So 2.05 squared minus 2 times 2.05 plus 1 is equal to 9.717625. Okay, so delta y is going to be the change between f of 2.05 minus f of 2, which is going to be equal to 0.717625. Okay, but now for differentials, right? For differentials, how much of a difference will it make? So if we take a derivative, so dy is equal to f prime of x dx, so that's equal to 3x squared plus 2x minus 2 dx. So we know that x is equal to 2, and dx, which is the step, is 0.5. So that means we will have 3 times 2 squared plus 2 times 2 minus 2 times 0.05. And actually, yes, this is 0.05. And that's equal to 0.7, right? So we are overshooting quite a lot. Okay, now if we do 0.01, right, 0.01, we actually will get closer. So for part B, right, for part B, let's compute f of 201, which is equal to 2.01 cubed plus 2.01 squared minus 2 times 2.1 plus 1, which is equal to 9.140701. So delta y, which is equal to f of 2.01 minus f of 2, is equal to 0.140701. Okay, and then for the differential, so dy, which is equal to f prime of x dx, is going to be equal to, so here is 3 times 2 squared plus 2 times 2 minus 2 times 0.01, which is equal to 0.14. So this is actually really, really close, right? Almost equal, right? This is almost equal. So this is about the same. So they are close by when we are really near the actual point, right? So the smaller the number we get, the closer we get to the the differential, right? So let's do one more example. Going to be last example. So example 4 on differentials. So the radius of sphere was measured and found to be 21 centimeters. Okay, with the possible error in measurement of at most 0.05 centimeters. What is the maximum error in using this value of the radius to compute the volume of the sphere? Okay, so we know that the volume of the sphere, we remember from the related rates problems, that it's going to be 4/3 pi r cubed. So we know if we find the differential, dv is going to be 4 pi r squared dr. Okay, so we know that r is equal to 21, which is the radius, right? Radius. And dr is 0.05, which is our error. So they change the dv, the change in volume, 4 pi times 21 squared times 0.05, which is about 277 centimeters cubed. So the maximum error of that sphere is in volume is 277 centimeters cubed, right? So this is the maximum error we can get. So although, the possible error may appear to be large, a better picture of an error is given by the relative error, right? So the relative error is actually something better, right, to think about rather than the numerical answer here. So the relative error would be delta v over v, or same thing as dv over v, which is equal to 4 pi r squared dr over 4/3 pi r squared, pi r cubed, which is equal to 3 dr over r. Okay, which is equal to 3 times 0.05 over 21, right? Which is about 0.007. So, which is, right, pretty small. So that is essentially 0.7% of its volume. So less than 1% error, which is a really, really good percentage. And in physics, that's pretty well numbers, actually. Right, perfect. So that would be it for the linear approximations and differentials. So next lesson, we're going to talk about the hyperbolic functions. Right, thank you, students, and I will see you all next time.